Okay, good morning, everyone. We are approaching the end of our summer session. Today, we're going to talk about search space algorithms and optimization. We'll start with exhaustive search, and then we'll move into some ways to prune that space, to try to reduce it. One thing to keep in mind is even though we're going to do some things which can improve the performance of algorithms, we are not going to solve NP completeness. So if a problem was NP complete going into this lecture, it is still NP complete going out of the lecture, and no one should try to make you think otherwise. Okay. So these are some of the design techniques that we have discussed in our course, more or less in order that we have discussed them. There are some other ones that didn't make it to this list that we've talked about. For example, we did something called transform and conquer. For example, if you sort the data and then you're able to do what you need to do with it. So that has a separate name. All right, so today we're going to look at these techniques at the end. Of course, exhaustive search is something we have seen before on many occasions. It's particularly relevant now as it's the only solution that will, well, I shouldn't say the only one that'll give you an optimal solution, but the other solutions that are there do not preclude an exhaustive search. Okay, so our focus is again on NP complete problems. Why NP complete problems? Because other problems that we tend to have better algorithms for. So what we're talking about here is problems where the search space is very large, right? Just as heads up, so you are not, I more or less finished the exam for Thursday, and there is no proof of NP completeness. So just you might appreciate that. All right, so how do we do this? Well, the first step is to find all the possibilities, right? So if we have to do exhaustive search, we have to try all possibilities, then we need to have a mechanism for generating all the possibilities, okay? All possibilities could mean all permutations, all combinations, right? Permutations means the order is important. In a combination, we're dealing with a set, the order is not important. And then we need to iterate over all those possibilities. The question is, can we cut down on the space? Can we avoid some of those possibilities if we know that they're not going to lead to an optimal solution? All right. So we may know that for one of two reasons, either because it can't lead to a solution at all, or it may lead to a solution, but we know that that solution will be no better than any of the solutions we have so far. For example, let's say we're trying to minimize cost. And if we go any further, it's just going to make the cost even more than what some other algorithm, another possibility already came up with. So obviously this one's not going to be better. So in that situation, we might as well back up and try something else. All right, so before we go any further, we need to explain what we mean by permutations and combinations, right? You should have seen those in 120 or 220 or maybe a probability course, right? So permutation is orderings of the data, right? The order matters, and if there are n items, there are n factorial of them. If there only are items, then they are n factorial over n minus r factorial, right? So the order matters. And here we have some code, right? We have some code that will do a permutation, right? If you are coding in Python, and I imagine there's something comparable in Java, right? There's a package that will actually generate the permutations for you, right? In Python, I think it's something called itertools for iterations. So there's code for that, all right? But let me explain to you how this code works, right? This line here is just Python for combining all the elements of a list, okay? So what is join is like the opposite of split. I think we've used split in some of the graph programs that we wrote, right? So join says, put it all together. And I think there's a space in between, but you could do a join without a space also, right? So put all the elements of a list back together again, exactly the opposite of split. And then what we're doing here is we are swapping two numbers, current number with whatever number is on the left. We call the permutation function recursively, and then we swap back. So that's how we generate permutations. Now, can anyone tell me what the time complexity of this is?
N factorial.
It's going to be n factorial at the least, right? At the very least, it's n factorial. Why? Because it has to be at least as long as the number of permutations. It may even be longer because of some of the overhead that's involved, but at the very least, it has to be n factorial. Right, so here is some Python. This was also Python, but this was Python the way we would code in Java or any other language. This is using some built-in Python tools to enable us to create the permutations with a permutations function on a list. And again, it takes at least n factorial. Keep in mind that it could lead to Stack Overflow. Stack Overflow, not the website Stack Overflow, but actual, as we saw in Python, it calls maximum recursion depth exceeded. And it's very easy to do that. Yeah, we saw that yesterday, right? We saw that yesterday as well. All right, what is combinations? Right, so combination is, it's also a set of elements, but in this case, the order of the set of elements does not matter. So what that means is basically taking a permutation and then dividing by the factorial of the number of elements in that, because that means that we don't care about the order. All right, and then we have a bunch of interesting rules about combinations. I don't think they're relevant to what we're doing here today, but those are just some cool rules. Okay. All right, and here is some code. This actually looks like a Java code, right? So here's some Java code to create combinations, and fine. And here is some Python code for generating the combinations, all right? But I want you to take a look at this, all right? Here we have a recursion tree, all right? So what are we doing here? Right, so this is obviously not the entire tree, but what are we saying? We're saying we have, this is, I guess, yeah, if you take a look over here, let me move this out of the way. I don't know what you see on your end. This is C53, all right? So what does C53 mean? C53 means I start with 5 items, 1, 2, 3, 4, 5, and I'm gonna take 3. Now, if I'm gonna take 3, that means that 1, 2, and 3 gonna have to be in at least one of them, right? So I can't do, can't have 5 different ones without 1, 2, or 3, all right? So on the assumption that I have 1 here, or 2 here, or 3 here, what can I do with that, right? How can I get to, right? So the leaves all represent a combination of 3 items out of 5, and it's showing you the different ways to get to that. Okay, so now we get to how this, applying this back to algorithms. Okay, so what is exhaustive search? Exhaustive search means to try all possibilities, and it's a process. So we create a candidate solution. Okay, what do we mean by a candidate solution? So for example, we're doing the traveling salesman problem. Actually, that's not a good example. Let's take the subset, the subset cover problem, right? Where we're trying to get a bunch of subsets, and between all of them put together, they cover all the items in the original set. So that's one of the examples we did in NP completeness. We might have also done it in approximation algorithms. So that's a good one because it's the combination that matters, right? There's no difference between, let's say, choosing S1 and S2 versus choosing S2 and S1, right? So the order doesn't matter. The set does matter. So we create a candidate solution. We see if it meets the constraints. So in the example of the subset cover problem, we see if I take all the elements in those subsets, does that cover the entire original set? Does it meet the constraints of the problem? And if it does, then it's a valid solution. Okay, if I want to get all solutions, right, as part of my exhaustive search, then I can continue through other ones. So what is the time complexity here? So as a general rule, we can say the time complexity is the number of different possible solutions, how many combinations in there, how many permutations are there, times the work involved in evaluating each candidate. Okay, I should also add that there's also maybe overhead in generating the candidate solution as well, right? So maybe we should, maybe I should even add that in. All right, so let's take a look at this example over here. This is an example that we've seen before in our discussion of NP completeness, right? So first of all, we want to differentiate between two terms, right? There's a Hamiltonian path and a Hamiltonian circuit. In a Hamiltonian path, we need to visit every vertex once and only once. In a Hamiltonian path, we need to visit every vertex and return back to, I'm sorry, in a Hamiltonian circuit, we need to return back to where we came from, right? So in this example over here, we go from A to B to C to D to E. So we've now visited every vertex, and that's it. We actually can't get back to A without repeating ourselves. In this case, we want to go, let's say, A, D, C, B, A. So that is a Hamiltonian circuit, right? In both cases, we like what we call a simple circuit, right? A simple path or simple circuit means nothing is repeated along the way either. All right, so here is the sort of pseudocode, right? To figure out if we have a Hamiltonian circuit, we generate another permutation. In this case, a permutation means an ordering of the vertices. And what do we need to do for each permutation? We need to check that each pair of successive vertices in the path is an edge, right? So if the permutation says do BD, we have to check, does edge BD exist? And we discover, no, BD does not exist. Everyone see that? So we would reject that particular case, okay? We have to check that there is an edge, and also we can get back. All right, so let's say we say we're going to go A, D, C, B. We have to check that there is also an edge from the end of the permutation back to the beginning of the permutation, right? So we have to check for that, and we have to, if all that is true, right? So each edge in the permutation or each successive pair in the permutation is in the graph, then good. We need to be able to go back to the beginning. If we have that, then we have a successful Hamiltonian circuit. Okay, so that's exhaustive search. We've talked about that before. The question now is, what is backtracking? How is it different than exhaustive search? And it will also be different than the branch and bound. So in backtracking, we start to create a candidate solution, but we don't necessarily evaluate the entire solution. We look at a little bit of it. And we look at that point, right? If we discover that this is not going to work out, then we stop. So let's put this in the context of Hamiltonian circuit, right? In a Hamiltonian circuit, first we generate a permutation. So let's just say the permutation was ACDBA. Right? And then we check, does that work? In this case, we say, hold on, we're going to go this slowly, right? A, D, C, okay, so go from A to D. Does that still work? Does that edge exist? If yes, let's take it from there. And as soon as we encounter a problem, we don't do the whole thing and say, well, that didn't work anyway. We immediately backtrack. So backtracking says, take one step, see, does it make sense so far? If it doesn't make sense, you stop, you back up. And it's a little bit like DFS. How is it like DFS? Anyone want to tell me why this is like DFS, depth first search?
In DFS, you can move back to the previous edge. like vertex.
All right, so in DFS, right, you advance to a vertex, and then you see where you can go from there. If you can go from there, if you can't go from there, either because there are no more edges, or because whatever edges are there, you are take you to vertices that you have already visited. So you back up. You back up to the vertex from which you came, and you see if I can try something else. So let's just be clear, backtracking is not DFS, but DFS uses a backtracking technique as part of its strategy, right? I'm going to repeat now what I said at the beginning of the lecture, and I'll probably say it again before we're done today, all right? Most of the problems to which we applied backtracking are NP complete problems, and it will still be an NP complete problem. So what does backtracking do? Backtracking allows you to take a problem, and instead of it being 2 to the n, it might be 2 to the n divided by 10, right? In other words, it allows you, it's not changing the search space, but allows you to cut back on some of the possibilities that you've seen. Okay, it is not a solution to NP completeness. Right, so here is an example of Hamiltonian circuits. Okay, so we have a function here called isSafe. Okay, what does isSafe do? isSafe checks, can I add this edge? Okay, can I add this edge to the graph? So let's look at what it does, right? So first of all, it checks this. Okay, what is the purpose of this line here where my mouse is? So let's work it out from the inside out. Okay, in the inside, we're saying, take where I am right now in the path and see, is there an edge from that point where I am right now to V? Okay, if there is no edge, right, because the adjacency matrix says it's 0, then return false. In other words, this is not a safe edge. I cannot add vertex V to my path because I cannot go from where I am right now. That's what this path thing is saying. This is where I am right now. I want to go to V. If the graph of that is 0, that means there is no edge. So I return false. Okay. That's one thing I need to check, right? Does this edge get me anywhere, right? Otherwise, I'm going to back up, right? Take a look at this code over here. What does this code do? This code checks, have I visited this vertex already in the path before? So if I've already visited the vertex in the path, then I don't go to that vertex, right? So you can debate, you know, do you agree with the order of these? Do you think this makes sense? So I have this if statement here and the for loop there. Would it work if I switch the order? The answer is yes. Should I switch the order? Does it make sense to keep it this way with these two statements here and then the for loop, or do you think I should do it the other way around?
This one is better.
Okay, why do you say that? Because I took the
Because I
code
want
from a
to-
website and that's probably correct, yeah.
Because I want to see if a vertex is adjacent to a previous vertex.
That's correct. Okay, there's no point in going through the whole loop to see if it's been used before, right? Because that's an order of n complexity here. If there is no edge, if the edge doesn't exist, there's nothing to talk about. All right, so I get more bang for the buck, as we say, if I do this first. Because otherwise I have to go through the whole list, see if it's been done, but I can't use it anyway. This says you can't use it, so don't bother with it. All right, so that's just a piece of this. That's not the whole algorithm. That was just a little piece. Now we see that little piece in context. All right, so let's walk through the code here. Again, this is Java code today. So this code says, okay, if the current position is where I started, okay, this V, it's a little, I'm sorry, I take that back. Okay, pos is not the current position. Pos is how, it is the current position, but it's the number of vertices, right? So once I've reached the number of vertices, when my position is the number of vertices, that means I'm basically done. So I'm only done though if what? If I can get back to where I started, right? So this is saying, right, go from the last position in the path back to the beginning of the path. And if there's a 1 for that edge exists. I can go in my picture here, right? If I can go from A to D to C to B and then back to A, right? That's what that code is doing. This is saying if I can get back to where I started, this is the last position in the path. This is the first position of path. If that edge exists, that's great, right? I return. All right. If not, then I got to try other things. Okay. Now there are 2 reasons why this might not happen. Right. One is, notice why I might land up over here. One is I'm not done yet. So if I'm not done yet, I have to continue on my path to see if I can get done. Right. The other possibility is that I'm at the very end of the path, but I can't get back to the beginning from there. Then that's also a problem. And it's going to return false, right? It's going to return false because it can't get back. All right, so this enables me to try different possibilities. So what does this code do? It says iterate over all the vertices except for the starting one, right? That's what I'm starting with, v equals 1. And I check is safe. Okay, who remembers what is safe does? That was the previous slide. So what was the purpose of is safe?
Like if the edge exists.
Okay, so first of all, I have to make sure that that edge exists. I can add vertex V, correct? That was the first 2 lines. And then what was the purpose of the for loop?
Adjacency.
The purpose of the for loop was to determine if I use the vertex already, right? So if the vertex already appears in the path in one of the prior positions, then I'm not allowed to use it. So this says the vertex has not been used before and it will get me to the next spot, right? So that becomes the next spot in the path. And then I call this function recursively and I see, okay, is it, what can I do from here? What can I do from here? And if the function ham cycle returns true, that means that this happened. That means I'm done. So I return true from here. All right. And that's the code. Okay. So that is a backtracking for Hamiltonian circuit. We're now going to do backtracking for traveling salesman. Okay, but remember, traveling salesman is what kind of problem? It's an optimization problem. What does that mean? An optimization problem means we want to find the minimum cost, not just, does it work, but what is the minimum cost, right? So keep in mind that we have 2 problems here. We have the optimization version, that's one I just described. What is the minimum cost of going through all the cities and returning back home? And the decision problem is, can I do this with less than or equal to some cost of K? And we proved in the NP completeness lecture that we can reduce this to traveling salesman problem, meaning if I can solve traveling salesman problem in polynomial time, then I could also solve the Hamiltonian circuit problem. Okay, so here is a backtracking, right? Backtracking applied to traveling salesman problem, all right? So take a look at this. This says, right, if we are up to, it's parts of it are going to look very much like Hamiltonian circuits because the problems are closely related. So this says, if the count is n, meaning if I have visited n cities now, and I can get from the last position, posits the last position of the n cities, back to 0, back to the beginning. Okay, now why does it say greater than 0 here? And over here it said equals 1. Is that just like different people coding style, or is there a reason for that? So we know Geeks for Geeks is not always consistent. Certainly other websites are not always consistent with Geeks for Geeks. So it's definitely possible that they're just making different assumptions, but there's another reason that is important to this problem.
Negative cost?
Not negative, but cost, okay? In Hamiltonian circuit, I don't care about cost. Everything is a 1 or a 0, right? Here, I care about cost. So it's not just a 1 or a 0. It's if it's greater than 0, that means there's an edge with a cost, right? Okay, so this is saying, and there is an edge there. So then that's good. Well, it's not so simple because I have to check. Is it not just is it good, but is it less than whatever I had? So answer is the answer I had so far, right? And the other possibility is I look at the cost at so far plus the cost of going from the last vertex back to the beginning. And I say, if this is less than whatever I had so far, the best answer I had so far, then that becomes the new min, right? So again, I'm not just returning true or false, yes or no, 1 or 0. I'm returning a number that represents the cost of the minimum circuit. Okay, what does this code do? Well, it's going to be similar to Hamiltonian circuit with its own little twist. So let's look at the code. All right, so I tried to find another vertex to add to the path. And I say, if V of I equals false, anyone want to guess what that's for? I check, has it been visited already? Okay, by the way, if you look at this code over here, this code did not bother with it. How does it check if it's been visited already? There's no V array here. There's a V integer. There's no V array. So how do we check in this code here whether
We check it in the for loop?
Check in the for loop by going through the whole path and seeing, is it in the path? So that's not really a very efficient way of doing this, okay? This code here is not very efficient. This code here is smarter about it, right? It keeps track, uses a little bit more space, you know, O of n space, but it keeps track has been visited like we've seen in other algorithms that we did. And we check if the edge exists, right? So we're saying, and I can go from wherever I'm up to this new position I. There's a cost there. That's a sign that there's an edge. And we mark it as visited. And then we recursively try to go from there and see what happens. Okay, notice what we're passing in as the new cost. Okay, so this position here is the cost. What is the new cost? It's the cost I had so far, plus the cost of the edge from my current position to the next position, right? So this becomes the new cost. I also need to keep track of the best cost so far. When I'm done with this, I mark it. This is where the backtracking comes in. I say, okay, I don't know what happened there. If it was good or bad, it doesn't really matter. But I now try something else. So when I try something else, I say we're going to mark that vertex as not visited because we're trying something else now. And then you need a calling code, right? So this code here is for the calling of it. So here's an example, all right? What I did is I just showed you basically the function arguments as over time, okay? So what does this represent here? This represents which things have been visited, okay? And you can see, right, what's going on. It also tells you, right, the cost of the path. Okay, this is the path so far, but remember the path so far, right, even though it looks like, wow, these are all less than that, but that's because we're not done yet, right? So this is saying, you know, as I work my way through the path, as the count goes up, right, what is my cost so far, not including that last edge, okay? And then we have the ANS value that keeps track of the best path so far. All right, now we get to branch and bound. Branch and bound is sort of a cool technique. And it says as follows, right? In the, what do we call it? The backtracking version, what did we do? We went as far as we could and we kept on checking, is the cost any, you know, is it less than what the best answer we had so far? right? In branch and bound, we try to be smarter about it. We look ahead and we say, what is the best that we could do? Which gives us, the best possibilities, and we're going to use that approach, all right? So we basically look at the cost of what we've done so far, plus an estimated cost for what we are still going to do. Does this remind you of anything from our course? So there's only one example that comes to mind where we did something like this. I wouldn't say we spent a lot of time on it, maybe like 10 minutes, but we did talk about it. I called it like a hybrid approach. So most of the stuff we did was not like this, right? We didn't sort of guesstimate how well something was going to work out. So that's why you need a lot of assignments in this course, a lot of programming assignments, because when students do programming assignments, they really start to understand it. So that's why we did not have an assignment on this. The A-star search. Remember the A-star search where we said something like this, right? F of n equals the G of n. Something like that, right? So we had the, sorry, that should be G of n. Right, where we look at the cost, the exact cost up to a certain point, and then the cost from there to the destination, right? So we had a hybrid. We said it was using like robots trying to find their way around. Okay, so again, a lot of these concepts are best experienced with an actual example. Okay, so take a look at this, all right? Now let's just move this out of the way. Okay. So what we're going to do is we look at it from the perspective of each vertex. All right. So from the perspective of each vertex, we look at the two lowest plus edges, the two cheapest edges. So how many edges does each vertex actually have? This is a complete graph, by the way. Can someone tell me how many vertices each one has? How many neighbors, I should say?
3.
3. So why am I looking at the two lowest plus edges? In other words, in Dijkstra's algorithm, in Prim's algorithm, we looked at the lowest cost edge, from a vertex. So we get that, right? We want to find the lowest cost. Or you could say, look at all of them. Why are we looking at the 2? Or is it something like partition and quicksort, where we looked at 3 and we took the middle of the 3? So the answer is it's not that. Why are we particularly interested in the 2 lowest cost edges? And the hint is this is the traveling salesman problem.
We want to compare the 2 costs.
Well, we want to compare them, but again, why 2? So a vertex could have 10 edges, right? So we're not saying, pick 10, and we're not saying take the lowest one. We're saying take the 2 lowest cost. Here's the answer. The answer is we need to go into a vertex and we need to go out of a vertex. I said it backwards. We need to go out of a vertex and we need to come back into the vertex. It's a circuit, right? We never go into a vertex and stay there. Every time we go out of a vertex, we eventually we go out of a vertex and eventually we come in. Okay, so it depends on what it is, right? If it's the starting one, we go out and eventually we come in. If it's any intermediate vertex, we go in and then we come out immediately, right? So we always need 2 edges. Everyone understand that? It's not obvious. It's not like anything else we've seen so far in terms of our calculations, right? So we need to take into account 2 edges. So that's what we do. We look at each vertex in the graph and say, what are the two lowest cost edges? Okay, so that's,
Professor,
yeah,
why can't we use the same edge? Why do we have to use
aha,
two
okay,
edges?
you tell me. Good question, you tell me. Because you're not allowed to use the same edge, right? Why can't you use the same edge? The answer is because you're coming from another vertex. So if I was, let's say, I think what Ilma's proposing is, okay, I left 0 using this edge of cost of 10 to get to 1. Why can't I use that same lowest cost edge to come back? And the answer is because that would mean that I'm coming from number 1. But I can't go and come from the same one because that means I'm repeating the intermediate vertex. Does that make sense?
Yes.
Right. So I always am coming from somewhere else. So if if I'm lucky, maybe this one's 10 and this one's 10, that's okay. There's no reason I can't have two edges with a cost of 10, but I can't have the same, I can't use the same edge twice. Not so much because you can't repeat an edge, but because you can't repeat a vertex. And when you repeat an edge, you are repeating a vertex. Right. So again, what we're doing here is we're going through each vertex. You find the two lowest cost neighbors. Right. So there's some data structures involved here. Right. How do I do that? But okay, we're not worried about that at the moment. And I do that for each one. Okay. So for 0, my two lowest cost edges are 10 and 15 with a total cost of 25, because I need to go out and in. For number 1, right, I have a cost of 10 and 25, total of 35. Okay, so this 35 is not that 35. This 35 here is the sum of the 10 and the 25. All right, I go from to go from 2. So from vertex 2, my lowest costs are 15 and 30. And from 3, my lowest costs are 20 and 30. Now keep in mind that these are lowest bounds. You know why? Because it's possible that it's possible that some okay, so it's possible that one of these calculations will end up reusing an edge multiple times, and we don't want to do that. So we will worry about that later. But that's why this is a lower bound, because it may be possible that not all these edges will work. Okay, so I add this up. Okay, I assume, right, I'm making an assumption here, and we know it's a bad assumption. It's a lower bound. That's what it's called, branch and bound, not branch and exact. It's branch and bound. It's saying, okay, so for each vertex, let's assume that we can use the lowest cost edges in and out for both. We add that up, and I divide by 2, or multiply by half. Why am I multiplying it by a half? How many edges does this sum reflect? And you can either correct, no. 4 is how many it should reflect, but how many does it reflect? 8, right? 2 edges here, 2 edges here, 2 edges here, and 2 edges here. So it's twice as many edges as I need. So what I do is I say, now divide that by half, right? Because for each vertex, I'm counting it in and out, but an in and out from one vertex includes an in and an out from 2 other vertices, right? So that's why I divide it by half, because this is counting stuff effectively twice. So I'm saying my lower bound is going to be half of that cost, all right? So what does that tell us? It's saying that at this point, I know that my tour means, going through all the vertices and coming back home, will be at least 75. Does not mean I can do it in 75. It means it's going to cost at least 75, not less. It cannot be less than 75. All right. All right, so let's see what we do with that. All right, so next up, so we start with vertex as 0, and now we have a choice. Okay, our choice is where do we go from here? So we consider the 3 other vertices and we say, what do we expect will happen for each of those vertices? Okay, so the yellow, the fact that this is highlighted yellow, that reflects that that was the answer. Okay, but we don't know that yet. So pretend that it's not yellow yet and that we're still deciding which option to take, 1A, 1B, or 1C. So we do some math. We take the old lower bound. What was the old lower bound from the previous slide? What did the previous slides say is the
75.
75 plus the best way to go out of 0, well, to go from 0 to vertex 1. So to go from 0 to vertex 1 is 10. Okay, so this is 0, 1 is 10. Plus subtract off, all right, this. Okay, so what does this represent? It says I have to subtract off the edge that I already used. All right, because part of that lower bound was going in and going out. So it's saying subtract off what I already accounted for in that 75 of going in and going out and divide by 2 because I'm going in and going out. So what does that come out to be? It comes out to be 75 for the lower bound, the edge from 0 to 1, and we subtract off the best edge going into 1 and the best edge going out of 1, which happens to be the same. So we divide that by 2 because we only need to subtract it off really once, and we get back to the same 75 that we started with, right? You'll appreciate this more when you see the other ones, okay? So the next option is to go from 0 to 2 instead of from 0 to 1. So you say, okay, my old lower bound was 75. Going from 0 to 2 is 15. So that's the 15. And then we say, okay, what's the lowest cost edge for 0? Subtract that off. That was already factored into the 75. So that's the 10. And the lowest cost edge from 2 is 15. So that gets added in here. We take the average of that. So this is 90 minus 12.5 is 77.5. So we're saying if I go from 0 to 2, my lower bound, my lowest bound, lower bound overall becomes 77.5. All right. Then I say, well, what happens if I were to go to 3? So if I were to go from 0 to 3, so I'd have my old lower bound plus the cost of going to 3, which is 20, plus or subtract off the average of the 2 lower costs from the 0 and the 3. So from the 0 was 10, and from the 3 it was 20. So I have the 10 and the 20. Take the average of that, 15. So I have 95 minus 15 is 80. So I said, which of those was the smallest? Right? Because what does this mean? It means if I continue going from to vertex 1, my lower bound is still 75. So that's good. If I go to vertex 2, my new lower bound is going to be 77.5, which isn't bad, but it's not as good. So we assume that I'm better off going with the 1 because it doesn't reduce my lower bound. If I go to vertex 3, we know that my lower bound is going to go up to 80. So we say, It doesn't look as promising. All right. So now we get up to the next iteration. In the next iteration, I went from 0 to 1. And now I have a choice. Where do I go from the 1? I go from the 1 to the 2, from the 1 to the 3. So I only have 2 options left. All right. And this one gets a little bit trickier because I have to do what's called a second min. All right. So I'll explain that to you in a moment. All right. So I take my old lower bound. What's my old lower bound?
75.
75. Okay. It's the lower bound from this page, not from this page, not from the beginning, but the previous iteration. Right. So it's 75 plus C12, or the cost of going from that current vertex to 2, which is C12 is 35. And the second min. So we look at not the smallest from 1, but the second smallest, which is 25. Right? Because 10 is the smallest. We already took care of that in the first min. previous iteration. So that's why we have to use the second one. And the second min from 2. So we look at 2, there are 3 edges. 30 is the, sorry, where did I get the 15 from? Oh, right, the second min is only from 1 because that's the one that it came from. Here we use a regular min. So I get the 15, 25 plus 15 divided by 2. So that's 40 divided by 2 is 20. So I have 75 plus 35 is 110 minus 20 is 90. Okay, so what that's saying is if I go from the 0 to the 1 to the 2, my lower bound becomes 90, which is maybe good, maybe not. What happens if I go from the 0 to the 1 to the 3? So I take my old lower bound, which is 75, right, from the previous page. I take the C13, which is 25, and the second min from 1, is 25, and the min from 3 is 20. So I get 25 plus 20 divided by 2, so 45 divided by 2, 22.5. 100 minus 22.5 is 77.5. So if I go from 0 to 1 to 3, my lower bound is only goes up to 77.5 instead of going to
0, 1, 2.
Instead of going, well, going up to 90, right? If I would have gotten 0, 1, 2. All right. And then once I'm at 3, my only choice left is what? I have to go to 2. So that adds another 30. And then I have to go back to 0 is another 15. So I have 0 is 10, 25 is 35, plus 30 is 65, plus 15 is 80. Okay. And then this just prints it out. Fine. Okay, so here are just some of the helper functions, right? So here we have a helper function to find us the first min, right? We iterate over a list and we find the smallest. We also have a function for the second min. So the second min, we have to check that it's not the first min, right? Okay, and then we have some code over here as basically what we just described. Okay, so that is, that's that. Okay, so we have 2 options. Okay, we could either just code this together for fun, or if people have questions about any old material, anything about the exam, I can answer those. Should we try to code this? All right, I have a question here. Any advice on specific things to study? Yes, I have some advice on that. All right, so you should you need to do a divide and conquer recurrence. Okay, so definitely study that. I'm looking for, I wouldn't say exclusively, but sort of, you know, recurring concepts. All right, so understanding not just sorting algorithms, but, you know, when you use different sorting algorithms and, you know, understanding the different kinds of sorting algorithms, things like randomization, things like data structures and how they relate to algorithms. So I'm looking for, you know, often, you know, broad topics that keep on resurfacing. I'm looking for what you might call comfort with the material, conversational, is there a noun? Conversational ability. They're able to talk about it. So more than, you know, little nitty gritty details, let's say the kind of stuff that you got in the TopBat review questions. But you do need to do a recurrence. One recurrence. And you need to know the master theorem, and you need to know how to test or formula once you get a recurrence. So again, it will be, it's on, you know, pen and paper, closed book, and it'll be broken up into 2 parts. Okay, so one part will be about 55 minutes. You have a 5-minute break, and the other part will be about 55 minutes. It's similar to older exams, but, keep in mind a few things, okay? So some of the older exams had a lot of, individual, little mathy things. So not so much about that other than the recurrence itself. The other thing is this final is our only, in-class exam. So whereas in the past, it was material was broken up into, let's say, 3 exams over the semester. So, there's less focus on, let's say if you looked at an old final, you wouldn't see, let's say as much about sorting. And if you look at an earlier final, your earlier exam in a semester, you wouldn't find stuff from the end. So it is, it's representative of the whole semester. Also keep in mind that in older exams, topics have changed. So I've changed the way I've taught the course. A few years ago, I never did parallel algorithms, for example. I spent more time on math for analysis of algorithms, and the course has gotten a little bit less mathy and more coding. There is one question that reflects sort of empirical performance. So understanding what we've been doing all semester in pretty much all of our assignments, maybe 6 of the 8 assignments, in terms of how do you test for empirical performance? So understanding that. What would that entail? Testing for empirical performance. Yeah, it's it's pseudocode, right? So understanding the infrastructure. So we develop the infrastructure in class, and there are different students work with that differently, right? And I can't necessarily tell when you submit it, right? So some students just take it off the Slack, and if they can run it, they can run it. If it doesn't run, they hand it in anyway, and they don't have output. Other students are coding in class as we code. So they're trying to do the same thing on their machine, and actually interesting things happen, right? Sometimes they don't indent something because they didn't realize if the other student was indenting, and then it doesn't work, right? So, but the point is they're making the effort to code and to try to understand what we are doing, and not just take the code off of the Slack. So I'm trying to gauge in that particular question, what people took away from the whole process. Were they running it like an automaton, or were they trying to digest it? Okay, so let's see. There are some questions that come up here. So we had a question like, so you don't need to plot anything. You don't need to tabulate it in a chart. You do need to understand how you build up that data, the timings. Okay, so you're not calling matplotlib on the exam. Okay, you're not calling table text on the exam, but you do need to understand how to get the data structure that has timings and has different algorithms if that's what you're comparing. Like merge sort versus improvised, and not improved parallel merge sort, right? Yeah, so those are kinds of things that you should know about. How much focus should we put on small details of each algorithm? So let's take your example. Understanding we got to 7. So you don't need to know specifically what those 7 subproblems are. For matrix multiplication, you do need to understand that you got down to 7 problems. So you were able to reformulate your divide and conquer 8 subproblems, the 4 quadrants and the 4 quadrants and the cross multiplication there, that using some clever mathematics, we were able to get that down to 7 problems. That's what you need to know in the context of this exam. Okay, do we have other questions? Want to try to code this together? Okay, what is meant by error bound? Oh, you're talking about in approximation algorithms? Yeah, okay, error bound. So we have metrics, right? Metrics are ways of measuring how far is our approximation going to be from the real thing, right? That's what we do. So we introduce three possible measures, not the only ones, but those are three common ones in use. One of them is an absolute number, right? So it's saying that the difference between the real cost and the the optimal one will be not more than some function, 5 times x. Okay, that's one possibility. Another possibility is what we call the ratio bound. That's actually the one that we use the most, right? So all the algorithms that we had were a ratio of 2, a ratio of 1.3, a ratio of 1.4, 1.7, right? Those are some of the ratios that we saw. We actually had one that was a log n. Okay, so that's a ratio. And then we also have a percentage bound, which is taking the ratio and putting it over the absolute and seeing it as a relative error. We call that a relative error. So I will just say this: computing those ratios is usually difficult math. That's the kind of thing that a person publishing a paper will work on over time. It's not the kind of thing that I usually can ask of you in an exam. You should understand how an approximation algorithm works. So if you have a problem that is very difficult to solve, what would be an approximate way to solve it? But coming up with how good the approximation is going to be, that is often more challenging. So just a little bit more on the structure, right? Again, it's in 2 parts. Each part will have 4 questions. They're each worth 14 points, okay? So basically you need to do 7 out of 8, all right? So that'll 7 times 14 will be 98, and there are 2 like sort of one point questions that are separate. So I would recommend that you do all 8 if you can, and then I'll take the best 7 of those 8. So it'll be 4 and 4. And again, one of them will be a recurrence, one on empirical performance, and 6 other stuff. So I would not say, I'm trying not to be out to get you on this exam. It is a little bit of a, just a sanity check that the work that I've been seeing in this semester represents you. The one on empirical performance can be on any of the algorithms we've seen. Yeah, but again, the question is not so much, in that question, it's about the mechanism, right? Understanding how to do it. So it could be, testing empirical performance of searching or sorting or matrix multiplication or shortest paths, but it's really about more general, right? What techniques do you use to do empirical performance testing? So it's about the mechanism, what I like to call the infrastructure or the template, right? Understanding how you do that in a systematic kind of way. You should bring your ID, by the way, writing utensil. So as I said earlier today, so the proof, I'm not asking a proof of NP completeness on the exam. I have enough other things, and that usually just becomes a memorization effort anyway. So. Do we have a class tomorrow? We're going to have a class tomorrow. I have to decide what to do, but we have a class tomorrow. As a side question, okay, this is a direct message to me, but you're asking during class, so I'm going to read during class. I see you have a lot of books in the background. Do you have advice on reading a textbook efficiently, thoroughly? That is a great question. Okay. So the answer is the days of textbooks have changed. You know, when I was your age, we had a textbook for most courses and we were expected to read it. And, you know, today, courses are different. So when I was a student, we didn't have slides. There were no slides. Professors wrote on the blackboard and you were expected to take notes, and that was it. There were no lecture recordings. There are no slides. So the textbook was a lot more important in those days. There was no internet to look up things. We go over a question that may show up on the exam. Well, I sort of described kinds of questions that are there. If anyone wants to share their screen and bring up a problem from the old exam, I gave you a lot of old exams. So if there's something that you've been looking at, you're curious about. Can you do a specific recurrence? We could do a specific recurrence. Okay, did you have one in mind? Yeah, so why don't you bring it up? Okay, so. Okay, this is a good recurrence. I mean, not that they're good and bad recurrences, but this is a relevant recurrence, okay? So it's the kind of recurrence I could ask you on our exam. Probably won't be exactly these numbers, but this style of recurrence, okay? So let's take a look, okay? The format of the question will be identical, meaning it'll have 3 parts. Use the master theorem, get a closed form formula, and then verify the formula for a number. And it's usually the next case after the base case, right? So if the base case is 1 or 0, so you look at what would the next number that would work well, right? So it's obviously going to be 3, because 3 divided by 3 will get you back to the t of 1. All right, so the first thing is we need to use the master theorem. So the master theorem, you need to find out what A, B, and C are, right? So A is the multiple. Can you put your pointer on the A? No, not that A. The A, no, not that A. The A in the formula. The implicit A. There you go. Right, so that 9 is the A. Good. Can you point to what the B is? Correct. Okay, there's your B. And you point to the C. That's the trickiest one. The C is the exponent. Very good. Okay, great. All right, so there's your A, B, and C. So we have to compute log A of B. So log A of B is 3 of 9. Log 3 of 9 is 2, and the C is 1. So the C is less than the log B of A. So that means that the dominant part is going to be the n to the log A of B, which is n squared. Okay, so can you point to the n squared in the solution to A? There you go. All right, so that is the order of magnitude. Okay, when you do part B, If you get an answer that is not O of n or theta of n squared, then you got a problem. It means something went wrong. Okay, you might not have time at that point to try to do it again, but at least say that. Okay, say, I know I made a mistake because I know it should be n squared and I didn't get n squared. So it's sometimes interesting. People get a closed form formula and they're testing it. So either they don't test it, they just they plug into the original equation. The numbers for the log will not be difficult to calculate. Okay, what do I mean by that? Okay, so sometimes it's a nice round number, like 3 squared is 9. Sometimes, let's say it's log base 2 of 7. Now, I don't expect you to be able to do log base 2 of 7 in your head. I can't do log of base 2 of 7 in your head. Some people could probably do a few digits, but that's it. But what you can do is this, right? You know that log 2 of 4 is 2, and you know that log 2 of 8 is 3. Did I say that right? Log 2 of 4 is 2, and log 2 of 8 is 3. So you know that log 2 of 7 is somewhere between 2 and 3. So without knowing if it's 2.6 or 7 or 2.8, you should be able to do that. So you don't need to, be able to do exact logarithms, and yet you can't do exact logarithms because they're transcendental numbers, right? But you should be able to, estimate it. Know between which two integers it falls. All right. So are we ready for part B? I assume that's the part you really wanted to review. All right. So the first thing we do is we make an assumption about n. We say n is 3 to the k. Why did we make n equal 3 to the k? Why not 2 to the k? Why not 5 to the k? The answer is because when we divide by 3, we want it to become k minus 1. So if I take n and I divide by 3, I get 3 to the k minus 1. And that's nice because it's going to enable us to do domain transformation. Okay, so that's why we did n equals 3 to the k. Now, how do we know that it's 3 to the k? We don't know that it's 3 to the k, but what we're doing is we're saying if it is of that form, and if it isn't, then we will be between two values, but that's okay. It's going to give us, it'll still give us the right order of magnitude. All right. So then we do a domain transformation, right? So what does a domain transformation mean? Domain transformation means, it means think of the function in terms of k instead of in terms of n. So we call the function s of k, and it represents t of n, right? So now what happens to our 9 times t n divided by 3 plus n? It becomes 9 times s of k minus 1. I already explained to you before that if I take n equals 3 to the k and I divide by 3, so I have n over 3 because is equal to 3 to the k over 3, which is 3 to the k minus 1. And if my function is in terms of k, so that becomes k minus 1. I also replace the n with 3 to the k. Good. Okay, I also need to worry about my base case. So when n is 1, what is k? Go back to the n equals 3 to the k in the previous line. In the previous line, and a one line up. One line right there, right? So if I plug in n equals 1 and I plug in k equals 0, they match. So that's why s of 0 is equal to t to the 1. If t to the 1 is equal to 1 from my problem, then s of 0 is equal to 1. You got it. Okay, great. So now we're ready for the range transformation. In a range transformation, I don't change the input. I change the form of the output. So instead of saying, just take s of k, I'm going to do something to that s of k. And I say, let's divide it by 9 to the k. Now, why did I divide it by 9 to the k? Why not something else? The answer is because I want to deal with that 9 that's in the front. Can you point to the 9 in the front of the equation? There. Correct. So now I say, okay. So I multiply the whole s of k thing by 1 over 9 to the k. And I say, okay, well, now what happened to the 9 times s of k? I divide that by 9 to the k. So I have 9 times s of k minus 1 divided by 9 to the k. That's like s of k minus 1 over 9 to the k minus 1. But 9 times s of k minus 1, I'm sorry, s of k minus 1 over 9 to the k minus 1 is the same as r of k minus 1. Okay, so that's where that r of k minus 1 came from. And I also have 3 to the k over 9 to the k. Everyone see where that came from? Can you point to that? So I had the, well, show them where it came from. So I had the 1 over 9 to the k on the left. Go to the left a little bit. That, and divide or multiply that by 3 to the k. I get 3 to the k over 9 to the k, which is the same as 1/3 to the k. Yeah, 1/3 to the k. Okay. So now what I do is I subtract r of k minus 1 from the other side. So in some of the newer solutions, I spell this out a little bit more. But basically what I'm doing is I'm subtracting r of k minus 1 from r of k. So you're not seeing here. I'm going to write it in the chat for a moment. Okay. So again, we've seen this a number of times here. 1 second. Oh, my screen isn't being shared. Okay. So again, what do we have on the left-hand side, right? Before we get to the r of k minus r of 0, right? We're going to have r of k minus r of k minus 1. R of k minus 1 minus r of k minus 2. R of k minus 2 minus r of k minus 3. R of k minus 3 minus r of k minus 4, all the way down to r of 1 minus r of 0. So if I add all that up on the left-hand side, what do I get? What do I get? Well, they all cancel out except for the first and last term. Can you point to the r of k minus r of 0? Go to the left, right over there. Beautiful. All right. So that represents the first term from the first equation and the second term from the last equation. So I get r of k minus r of 0. Now, where did the other stuff come from? Well, on the right-hand side, what do I have? I have 1/3 to the k in the first equation, 1/3 to the k minus 1 in the second equation, 1/3 to the k minus 2 in the third equation, 1/3 to the k minus 4 in the fourth equation, and so on. So what kind of series is this? I don't think I wrote it here, but what kind of series is that? That's a geometric series. That's a geometric series with a ratio of 1/3. So I have a geometric series, and the formula for the geometric series is I take a, which is my first term, put that on the outside. I take my ratio, which is 1/3, to the k, right, which is, it's going to be one more after the last term. So last term says k minus 1 in the summation. Can you point to the k minus 1 in the summation? Right there. Yeah, no. They're right there. You see that k minus 1? So the power is going to be one more than that. Point to the power. Keep going. No, not that power. They're right there. You see? Right there. Exactly. Okay, minus 1. And on the bottom, I have r minus 1, r being 1/3. And then I manipulate that, right? So what did I do? I took the 1/3 minus 1 on the bottom, which is minus 2/3. And that becomes 3/2 on the top, plus flipping the sign on the top. Okay, so that's where all that came from. And then the 1/3 cancels out with the 3/2 to give us 1/2. I have 1/2 times 1 minus 1/3 to the k. Okay, but now that's my r of k. Actually, I take that back. That's r of k. That's r of k minus r of 0. So I move the r of 0 back to the other side. What is r of 0? R of 0 is equal to s of 0 over 9 to the 0. 9 to the 0 is just 1, and s of 0 is 1, so it's just 1. So point to that 1 there. Go up 1. Oh, no, come further down. Go, just stay one place so I can already, okay, go down 1. Move to the left. Left. Keep going, one more, a little more. Right there. You see that 1? No, right there. That one. No. Go right there. Stop. That 1 is the one that came from the r of 0, right? And then I take the 1/2 times 1 minus 1/3 to the k that I got from the previous line, and I add that in. So I have 1 plus 1/2 makes 3/2. Show everyone the 3/2, continuation on that line, right? 3/2, good. And the half multiplies throughout, so I get 1/2 times 1/3 to the k. Now, that's my r of k. On the next line, go to the next line. I multiply r of k back by 9 to the k to get to the s of k. So I multiply through the 9 to the k. And what happens there is I just land up with the 9 to the k at the beginning, but at the end, it gets more interesting. Because at 1/3 to the k, times 9 to the k becomes 3 to the k. Can you show everyone the 3 to the k at the end there? There's my 3 to the k. All right, so what do I do? The 9 to the k and the 3 to the k are a little ugly. So I say, well, what is 9 to the k? Well, let's start with the 3 to the k. That's easier. So k was log 3 of n. 3 to the log 3 of n is the same as n. So go to the next line. You see the 3 to the k? 3 to the k equals n. Because k is log 3 of n. So 3 to the log 3 of n is the same as n. And if I take 9 to the k, that's the same as 9 to the log 3 of n, which is the same as 9 to the n to the log 3 of 9, which is n squared. So I plug those back in. So I have 3/2 times n squared minus 1/2 times n. And then I just factored out the half. And then you plug back in. So you plug in. And you say, okay, what happens when n equals 3? So 3 times 3 squared is 27. Minus n is minus 3, gives me 24. 24 divided by 2 is 12. And you compare that to what you got from the original formula. So in the original formula, I got t of 1 is 1, times 9 is 9, plus 3 is 12. So they should match. If they don't match, well, something went wrong. And say so. Say so.
Professor,
Yeah.
I have a question about when you get
Just before I'll take your question in a moment. I'll just say that if you want sort of help working through these, the solutions for my last 2 exams are more elaborate. So it's the same kind of question, but I do a little bit more step by step. And these solutions here, combining more steps. So I think the later solutions are a little bit better in terms of showing you the step by step. So it's the same kind of techniques. They all involve a substitution, a domain transformation, a range transformation, telescoping. Usually there's a geometric series, then you got to work backwards, plug your way back, right? So they all tend to have the same things in them. I'm not going to throw you a curveball in terms of the kind of question, but again, the 2 more recent solutions are a lot more detailed. Okay, I cut you off. I think it was Cheng speaking.
Yeah, that's me, because I did the question you posted for the other recurrences. So it seems like when you do telescoping for the summation, saying the RK minus R0 part.
Yeah.
Sometimes you do I from 1 to K, sometimes you do 0 to K minus
So
1. That's the same thing.
Okay, that's a fair question. So the formula is supposed to start with 0. I equals 0. That's the way the formula is designed. So you want to sort of get it into that form. And then if it goes up to K minus 1, then your formula, you're going to use K. If it goes up to K, the formula is going to have K plus 1.
Yeah, but I get it. But in this case, how do we get like 0 to K minus 1? Because
I'll tell
like
you why. So can you go down with your mouse to that formula geometric series there? Go up 1 right there. Okay,
Yeah,
I factored out the 1/3. So by factoring out the 1/3, my power went instead of it being. Now, by the way, I don't know if that's an I or a J. It looks a little inconsistent there.
That's a J, I think.
It's just a J. Okay, it should be a J. I try not to use I in my answers because both Word and Google have ways of converting lowercase into capitals, and it's very annoying. So it doesn't do that with I. It doesn't do that with J. It does it with I because it thinks you're trying to say capital I.
Oh.
By the way, I have to thank one of my former students. I think it was a student in the summer of 2018 or 19. Maybe it was 2019. So I used to have all these individual exams and all these individual solutions, and then he took all of them and organized them in that nice little PDF. So it used to be a big.
So in this
Okay,
case, you
math.
use the technique to factor out the 1/3 to get to the 0 start. Is that
Yeah, I
the
mean,
case?
I did that. He didn't do the solutions. He just organized it into one PDF document. But
Oh,
yeah, that's what I did, right? I pulled out the 1/3 and now it goes down to 0, so I can use the formula.
okay, because we used on the
Just one
other.
thing, just one thing to keep in mind. So on the left-hand side there, you have R of K minus R of 0, right? Can you point to that? On the left-hand side of the equation there. No, the left, go to the left, right over there. Good, beautiful. Okay, so R of 0, you have to find out what it is. In some cases, R of 0 is going to be equal to Chi of whatever n is 0. And sometimes it's 1, it could be 2, it could be a lot of things. So you have to always go back to the beginning of the question and find out what it's equal to. Okay, so sometimes it'll be 0 and then it just falls out. Sometimes it's a different numbers. Yeah, we have to look at the base case. That's where the base case shows up. That's the only place where you actually use the base case in this whole closed form solution. Yeah.
No, that's it for me. Because you, I think you use some other technique like +5, -5 on the other recurrences.
That's right. So I did that on one exam. Because remember, you can always add something into a summation as long as you subtract it back out somewhere else.
All right, got it.
So the idea with all these things is you make it work. Okay, you can't cheat, but you make it work. So if I need to add something to make it work, that's fine, as long as I subtract it somewhere else to make it even. That's what we're doing with these domain transformation, range transformation. We're trying to do it in a way that's legitimate, but also makes it work out for us. What's that problem below? That looks interesting. Okay. Aha. This is an interesting question. All right, so you're supposed to figure out what it's doing here. Right, so in this case, right, insertion sort, that's sort of a hard question on the spot, right? You have to figure out sorting the left portion, right? The right portion is unsorted. Radix sort, it's going by 1 digit. So yeah. Okay, you're not getting that question on the exam, don't worry. All right, was there another, you like that question? All right, could we do the final question on the winter 2022 exam? Okay, what was that? You want to bring that up for us?
If you want to try to bring it up, I think I have it.
Should be in the Google Drive, winter 2020.
So the final or the midterm?
I don't know. Final. So I'll just say this exam was a little different because they were at home. And therefore, it was assumed that they had access to everything. So I had to come up with something that was not just, material that we had done before, but something very different and creative. So it's not, this question is not really representative of what you would need to do, right? So what you need to do in your exam is more a sanity test on what you've learned in the semester, but we can look at it anyway. We can talk about it briefly. So go down, what was it? Go down to the question? Yeah, is it this? Or I think you said the last question. Go down further. Okay. Oh, so the bin packing problem, right? So NP completeness. All right, so in this case, they were looking something up during the exam and trying to understand how an NP completeness works. So you're not going to be asked anything like that. Write an approximation algorithm for the online version of BPP. All right, so what is an online version of BPP? What do we mean by online version?
The elements are coming one at a time. You don't have access.
Elements are coming, all right, as they come. The randomly considers up to 3 partially filled bins. And if none have room, then create a new bin. Okay, so this is different than the ones we did in class, right? So just so you understand, that semester, that course, one of our assignments was on bin packing. It was actually a cool assignment. I gave them random bin data and they had to figure out how many bins the different algorithms would come up with. So it was a sort of a cool assignment. So this was a variation because remember how the next fit works. How does the next fit work?
If the element doesn't fit in the current bin, we choose the next bin.
Correct. Okay, so basically you're always working with just 2 bins, either the currently populated one or a new empty one, right? So this one is a variation, right? You're not looking at all the previous bins. It's not like the first fit or the best fit. So it's like a variation on that, okay? So again, I was giving them something that they're not going to find on Google because I know they're using Google, so they can use resources. But the idea is not just to reproduce what someone else has up there, right? So with 3 partially filled bins, what are you doing? So you could have a data structure for that. We don't really need a data structure for that, right? You don't need a heap or some kind of min array, right? So you just check which of those 3 has the, what does it say here? I guess if none have room, right? So basically you could check any of those 3. Right, so you look at the remaining capacity of each one and you see if it's greater than what you have, then use that, otherwise create a new one. So you don't need any, I said a heap, but it's actually the binary search tree that we use more than the heap in the algorithms we did in class. What modification to your solution in B would you recommend to solve the offline problem? So what is the offline problem? So in the offline version, you have them all up front.
So in that case, we can use best fit or first fit. First fit.
Well, it's not so much the best fit versus the first fit. What do we do with the data to help us with the best fit or the first fit? It's a 4-letter word, and it's not a bad word. You might think it's a bad word after 6 weeks of this course, but you sort them, right?
Yes, sort them.
Okay, so you sort the values of the sizes, and then you can easily, match the different, the remaining size to what you need, your current need.
Right.
Okay, so then question D, that was an interesting question as well. Right, so what do we know about error bounds? Well, we know as a general rule, your upper bound is the number of items. Right, that's upper bound is the number of bins. And the lower bound, we said, is the total weight divided by the capacity. Right, but we also know more specifically that some of the algorithms that we have are 1.7, 1.4. I think we got down to even 1.22. I think there was 2/9. Okay, so where does this fit in? That's really the question. Where does this fit in that range? So we know, with the next fit, we did 2. Right, it was 2 approximate. And with the better algorithms, if it was done properly, we could get it down to like 1.3, let's say. So this is it's not as bad as next fit, and it's not as good as the first fit or the best fit, which means that it's going to be somewhere in between, probably closer to the 2 than the 1.3, but less than the 2, right? Because you have 3 bins to choose from rather than just 1. So that's also, part of, being able to reason about algorithms is to say, listen, I know what my upper bound is, I know what my lower bound is. I should be able to be in between that. Just like, for example, with Fibonacci, right? So we did a very complex analysis. Actually, we didn't do it in our class. We never really solved it. I do it in 220 because we spend actually more time on solving recurrences there. But using the method of characteristic equations, you can come up with the closed form formula for Fibonacci. But what did we do in this class? We did a bound, right? We said that the lower bound is 1.4 to the n, square root of 2 to the n. Upper bound is 2 to the n. So we know that Fibonacci time complexity is somewhere in between that, and it's a close bound is 1.6 to the n. So that's an important part of this course, and really life in general, is being able to come up with balance. So a big task that you're going to have when you go into the working world, and we do it with school also, right, is figuring out how long something's going to take. Right, you're never gonna know exactly how long something's going to take, but you should be able to use previous estimates of things that you've done to figure out, this is going to take me an hour, it's going to take me a day, it's going to take me a week, it's going to take me 6 months. Right, so being able to estimate that. The same thing with costs, right? How much money am I going to spend this year? So barring any crazy medical situation or something like that, how much do I spend? You should be able to estimate things like that. So I wouldn't say that's the purpose of this course, but it's a skill that does come up. Why don't you go up a little bit? Look at the previous question there. Okay, why don't we talk about that for a moment? So you did a project on that, right? Shortest distance between all pairs in a graph and state the algorithm's respective time complexities. Okay, so what are some of the ways to do that between all pairs? Just did a project on that. I'm about to mark that project.
Floyd, Dijkstra.
Okay, so we have Floyd's algorithm, right? Floyd's algorithm is designed for all pairs shortest path. Very good. And what technique does it use? What algorithm design technique?
Dynamic
programming, correct. Okay, and what's its time complexity?
M plus N.
V cubed.
V cubed.
Floyd's algorithm is V cubed. Okay, so that's Floyd. All right, next. What's our next technique? The Floyd is 1. That's the best answer because that's designed for this. but it's not the only possibility. So you did, again, you did a project with this. So you did 4, if I'm not mistaken, right? You did 4 algorithms, or 3, but 2 were variations on implementation.
Dijkstra?
Okay, so Dijkstra's algorithm is actually was originally written for single source, single destination, but it also works for single source shortest path, which is what we taught it for. And then if you run that for each vertex, you get all pairs shortest path. Correct. So what time complexity do you get there?
Depends on the implementation.
It depends on the implementation, right? And how so? So let's start with a basic implementation using the adjacency matrix and some kind of array to find them in.
V squared.
It's V squared for the basic Dijkstra, and then multiplied by V to do it for all V vertices. So that gives you V cubed. V cubed. Okay, so it's V cubed, but it gets to the V cubed differently than the way we get to it in Floyd, right? So here's one difference. In Floyd, the outer loop, so obviously you're gonna have 3 nested loops, otherwise you're not gonna get V cubed. In Floyd, the outer loop is the intermediate vertex. And if I do a nested, Dijkstra, the outer loop is going to be the starting vertex, right? The starting vertex is, we're going to iterate over the starting vertex called Dijkstra on that starting vertex. Okay, so that's your V cubed. And you said something about implementations. What are some of the other choices of implementation?
We can use a table instead of a matrix.
All right, so we can use an adjacency table instead of a matrix. All right, and that's usually paired with what other change?
The way that we use the heap to start.
We use a heap, a regular binary heap, and that cuts down on the time of finding the min and the time of updating. So we get those down to logarithmic time operations. So for Dijkstra, it comes out to be V log V plus E log V. Multiply that by V for all the starting vertices. So the upper, the dominant term will be V times E log V. Again, just to be clear, we're using Dijkstra not in the usual way. Normally Dijkstra is to solve the single source shortest path. In this case, we're using it to solve the all pairs shortest path, because that's what the question is, and that's what the question was in your programming assignment. Another way to find shortest distance, and then we'll stop.
Bellman and Ford on all vertices.
Say it again.
You can run Bellman-Ford on all vertices.
Bellman-Ford, right? So Bellman-Ford is also for the single source shortest path that uses dynamic programming. It also accommodates negative weight edges, though not negative weight cycles. And we can run that for all vertices. Okay. So then there's a question here about parallelization, right? Certainly for the Bellman-Ford and the Dijkstra for all algorithm, it's very easy to parallelize that at least 1 layer's worth, right? Because you just run that for each starting vertex. Floyd is a little bit trickier. You don't want to parallelize that over a K, because that's your intermediate vertex. That's not going to work. You can't change the intermediate vertices. What you could do is you could probably parallelize all the pairs inside that, the I and the J on the inside. That would lend itself well to parallelization. Okay, we're going to stop here. And we'll see you again tomorrow. See everyone again tomorrow.
Thank you, Professor. Have a nice day.
Okay. The last assignment, that's the one we did in class. What the one, yeah, just finished that up. That's like, we did what, 18 out of 20? Just do 2 more. Then with it. Just Google recurrence relations, add 2. Okay. All right. Take care, everybody. Bye-bye.